Hey everybody, we're going to look at a very powerful rule that you can use when evaluating integrals. It's going to help a lot of the time. It's essentially, it's kind of like the chain rule in reverse. So it's like the antiderivative of the chain rule. The idea is if you find some portion inside your integrand that is some useful, like if it's useful to replace some little function of x in your integrand with a u, or we usually use u. So u is going to replace some little function of x. Then we can use the fact that you basically use the principles of the chain rule. So if, for example, just to kind of get this idea, if u is some function of x, then f prime of x is going to be du over dx. In other words, du is going to be f prime times dx. This is the principle with these differentials, to replace the differentials here. So in this case, we're actually going to call u like it's some like function, some g of x, because f is going to be the main thing that we're integrating. So if you can isolate something, say I'll call that little function of x, call that g of x. I'll replace it with u. As long as u is differentiable. It's differentiable, and its range is an interval on which the f is continuous. Then you can make this replacement. So you replace the u in here. And remember, we said g prime of x dx is going to be du. So this becomes f of u du. Now this probably seems a little weird. Let's look at examples. It'll become more clear. Okay, we're going to take a look at this function, this one we're trying to integrate, which looks like a big old mess. The thing we realize is we can see out here this x to the third, and that's the derivative of x to the fourth, differing only by a constant. So if I say, well, if I call this thing here, call it u, so I'm going to call u of x this x to the fourth plus 2, because I know how to integrate the cosine function. And so so du over dx is going to be 4x to the third. And what we're actually going to use is this substitution. Du is going to be 4x to the third dx. Now, notice I have an dx and I have an x to the third, but I don't have a 4 there. How can I create a 4? Well, I can put a 4 there as long as I can compensate for that by dividing by 4. That's allowed. 4x to the third, and then I have the cosine of x to the fourth plus 2, and then the dx. So I've got all the pieces. So there's going to be my u. Here and here, those are going to be my du. So this becomes 1/4 integral of cosine of u du. What's the integral of the cosine of u du? That's going to be the sine of u plus a c. Because I don't know. I mean, I'm finding the general, the indefinite integral. And I should note, what is u? U is x to the fourth plus 2. So let's actually put that back in place. And so we've found the indefinite integral using a substitution. All right. Here we've got another one. Let's see if we can do something with this. By itself, this is too difficult to tackle, and the natural thing to do is to take this thing that's inside here and call that u. So I'm going to say u is going to be 2x plus 1. So then I'm going to jump straight to this step. Du is going to be, it's going to be 2. The derivative of 2x plus 1 is 2, and I'll put the dx there. And so I'm going to make this replacement. Now the problem is I don't have a 2 there, so what I'm going to do is I'm going to put the 2, I'll put the 2 next to it, so I have the square root of 2x plus 1 2 dx. But I can't make a 2 out of thin air. I have to compensate for it. Okay, so then I'm going to make the replacement. It's going to be 1/2 integral of, instead of writing this u to the square root of it, I'm going to put u to the 1/2 du, right? This is my du. Well, the integral of u to the 1/2 using the power rule, it's going to be u to the 3/2, and I'm going to put a 2/3 out front, right? That's the way you do the power rule in reverse. You increase the power by 1, but then you subtract, and you divide by that exponent, which is the same as multiplying by the reciprocal, plus a c. A few things will cancel a little bit, and so this is going to be 1/3 square root of, I can do the square root cubed of 2x plus 1, that's legal, plus c. That's my indefinite integral using a substitution. It's always good for these indefinite integrals. You want to go back to the x's afterwards. You want to go back, replace the u with your x. So you can see this u it's just a helper to get us where we need to go. But we don't want to keep things in terms of u at the end. Okay, let's take this one. Now we have this function where we have this ratio. It seems natural here to let u be the 1 minus 4x squared, because we can see the derivative, or at least a scalar multiple of the derivative, is sitting in there waiting for us. It's the x, all right? Because du is going to be negative 8x dx. And here's another technique you can use. I'm just going to, since I have an x dx, I'm going to write x, dx. What's that equal to? It's equal to negative 1/8 du. And so I'm actually going to make that replacement. This is going to be, I'm going to replace the x dx with negative 1/8 and a du, and then the rest of it is going to be 1 over the square root of u. In fact, what I'm going to do is write this as negative 1/8 u to the negative 1/2 du. So let's take the integral. So we're going to have negative 1/8, and we have u now to the 1/2 power, and I'm going to divide this by 1/2, which is the same as multiplying it by 2. And then I'm going to add a c. Now this is going to be negative 1/4 square root of, what's the square root of u? It's the square root of 1 minus 4x squared plus c. And there we go. That's my indefinite integral using a u substitution. Okay, another one. We got, of course, we know the integral of e to the x is e to the x, but what's the integral of e to the 5x? Well, it seems natural again to let u be 5x, okay, because I know what the integral of e to the u is, but du is going to be 5 dx. So dx is 1/5 du. So this is going to be 1/5 integral of e to the u du. I've just replaced all the parts. And we're going to, of course, have 1/5 e to the u is our answer, plus a c. Of course, we want to go back in terms of x. So this is actually 1/5 e to the 5x plus c. And there we go. That's it. Okay, now for tangent, this is something that you could probably look up in a table or something. What's the integral? But what's useful here is to remember that the tangent is the sine of x over the cosine of x. Now, why this is useful? Well, it's because I know the derivative of the cosine is negative sine, and the derivative of sine is cosine. It might be natural to think, oh, I'll let the numerator be u, but the problem is you need your du to be basically in the numerator. So the only thing I can do then is to let u be the cosine of x. Du is going to be, of course, negative sine x dx, which since I have a sine x and I have a dx, that's negative du. So the parts I'm going to replace then, I've got, this is going to be negative. I've got the sine x dx is going to be du over u. This might not look super nice. I'm going to write this as negative integral of 1 over u du. Some people like that, the way that looks better. I kind of do. Because I know the antiderivative of 1 over u. We know a function whose derivative is 1 over x, right? Or 1 over u. And that's the natural log. This is negative natural log of u. Now the thing about natural log is, of course, it's not defined for negative numbers. For the moment, I'll put it like this, but I'll put a plus c. The tangent function is what was it? It was no. U is cosine of x. So this is the negative natural log of the cosine of x plus c. Here's the thing we have to do for this. Because the cosine can be go from -1 to 1, I have to put the cosine of, some people put the cosine of absolute value of the cosine x, because this is the, we're only going to, oh yeah. Yeah, so remember also that the thing about logarithms, we can actually take the negative sign as the coefficient and put it as a -1 exponent on cosine. This is the natural log of the cosine of x to the -1 power, not the inverse, but that's just like to the -1 power, which is actually the natural log of 1 over cosine, which is the secant of x plus c. So this is actually a fact that we have. The integral of the tangent of x, that's the natural log of the secant of x plus some constant. So this is something that you can use as a shortcut anytime you see it again in the future. Now, what if we have a definite integral? What we need to do is to use the same substitution on the bounds, the lower bound and the upper bound, and then we evaluate it, not with the original bounds on x, but the bounds in terms of u. So this is the what I mean. So those bounds have to go through the same conversion function that x went through. All right. So let's look at an example. You'll see exactly what I mean. So we're going to integrate this function. From 1 to 2, it's dx over 3 minus 5x squared. It's natural, of course, to let u be the 3 minus 5x, right? And du is going to be, of course, -5 dx. Okay, so dx is -1/5 du. I can make that replacement. Now this here, u is g of x, right? So I'm going to write g of 2 and g of 1 as the bounds, and I'm going to have a -1/5 du, so that's part of it, and then I've got 1 over u squared. Now, what is g of 1 and g of 2? G of 1 is 3 minus 5 times 1. What's -2? And g of 2 is 3 minus 5 times 2. That's 3 minus 10. That's -7. So this is going to be the -1/5 integral from -2 to -7 of, I'll write here, u to the -2 du. Okay, the issue I have with this is a lot of negatives. And remember, if you swap the bounds, you will change the sign of the integral. So what I'm actually going to do is write this as 1/5 integral from -7 to -2 u to the -2 du. Okay, so now the lower bound actually is less than the upper bound. So we can evaluate this. We use the power rule, right? We're going to have u to the -2 plus 1. That's going to be -1, but we're going to make that negative, right? Because we have to divide by the exponent divided by -1. That's just negative. Okay, so we have -7 up to -2. And so we're going to evaluate this whole thing. We have 1/2, and then we have negative. That's u to the -1. That's 1 over u. That's 1 over -2 minus -1 over -7. Now there's a lot of negatives all over the place, but what we have here is this is 1/5 times 1/2 minus a minus a minus 1/7. That's minus 1/7. That's 1/5 times, let's see, that's going to be 7/14 minus 2/14. That's going to be 5/14. 1/5 times 5/14 is going to be 1/14. And that's my answer. Okay, now let's take this one. If we are trying to, now this one might not seem so clear. What are we going to do? Notice with this, the derivative of the natural log is 1 over x, and there's a 1 over x sitting right there, right? This is actually the integral from 1 to e of 1 of the natural log of x times 1 over x dx. This is actually perfect. This is setting up. So u is, g of x. That's the natural log of x. So du is 1 over x dx. It's just sitting there. So we can make the substitution, but I'm going to have g of the upper bound and g of the lower bound of u du. What is g of e? G of e, the upper bound, that's the natural log of e, that's just 1. And g of 1, that's the natural log of 1, that's 0. So this is actually the integral from 0 to 1 of u du. Which I know this is going to be 1/2 just from a geometric standpoint, right? Because if you have a function, this is the function, the function like y equals, if this is like the u-axis and this is the y-axis, y equals u is this line, and the area under here, that's 1/2. But of course, you can do this just by using the power rule. This is going to be u to the u squared, and then it's going to be 1 over 2 from 0 to 1. This is just going to be 1/2 times 1 squared. It's just 1/2. Minus the 0 on the lower bound, but that's just going to be 0. There you go. Very cool. Now, if you have some symmetry, if you have a function and we're integrating over symmetric bounds, then if your function is even or odd, then you can use some shortcut. So if for even functions, I'm going to draw like a little generic even function, and let's do a little generic odd function. Of course, not perfect, but even function, I can just do whatever I want here, and let's just copy that. Well, that's what an even function is all about, right? If I was taking an integral from, say, negative a to positive a, right? So now we're looking at the area under this curve. I think you can see the area shaded over here and the area shaded over there, they're equal to each other. So instead of just integrating the whole thing by symmetry, we can just integrate from 0 to a and double it. Now, if the function is odd instead, now odd functions are always going to pass through the origin, and so I'm going to if I were to integrate this from, let's say this is negative a, and then that would be a, of course, the area under the curve, if we were to, if I'm going to put the positive areas in green, let's say the negative areas, I'm going to put them in a yellow. Of course, you can see that the positive, the negative, the positive, the negative, it all equals out. You're going to get 0. So integrating odd functions over symmetric bounds, it's going to be a 0 area. The integral of an even function over symmetric bounds, you can just double the integral from 0 to the upper bound. So let's look at that, use symmetry. So what this is, so this function here, x to the 6th plus 1 is even. To check that, just evaluate if this is f of x, what's f of negative x? You're going to get negative x to the 6th plus 1. Well, that's just x to the 6th plus 1. That's f of x. So any negative value you plug in, and you're just going to get f of the positive value. So this is actually going to be the integral 2 times the integral from 0 to 2 of x to the 6th plus 1 dx. So saves it's a little bit easier because rather than having the you'll see what I mean, having one of the bounds be 0 is always nice. So we're going to have x to the 7th over 7 plus x. We're going to be integrating from 0 to 2. It's just a matter of plugging in 2. This is 2 to the 7th over 7 plus 2. And I'm going to just leave it like that. Because, of course, when you plug in 0, when you subtract this evaluated at 0, well, it's going to be 0 here because it's a polynomial and there's no constant terms. Take this, for example. What we have here is the tangent of x over 1 plus x squared plus x to the 4th. Now the thing about polynomials, if all of the powers are even, it's an even polynomial. And the tangent of x, this is an odd function. And if you don't remember that, what's the tangent of negative x? It's going to end up being the negative tangent of x. And it's because the sine is an odd function. Anytime you have an odd function divided by an even function, you're going to have an odd. It's going to be odd. If you have odd times an odd function, you're going to end up with an even function. If you have an even function times an even function, you get an odd function. But you have an odd times an even, or an odd divided by an even divided by an odd, it'll be odd. So because this is odd, and because we're going from -1 to 1, it's going to be 0. That's it. Okay, so we've seen how to use the substitution rule and then a couple other little tricks to handle integrals. The symmetry trick isn't substitution, it's just a handy trick to save some time. The substitution rule can get you far, but the rest of there's much more sophisticated tricks to handle more complicated integrals that can't be done just by the chain rule. One thing you might be wondering is, well, what if the chain rule, I said chain rule, by substitution. Substitution is, in essence, you take the idea of the chain rule and apply it to integrals. You say, well, what's the chain rule kind of going backwards? You might think, well, what about is there something you can do with the quotient rule or the product rule going backwards that could help you evaluate integrals? And it turns out there is. The product rule leads to a very cool rule for integrals, but we're not going to get into it here. It's called integration by parts, but that's a lesson for another day. And if you're doing Calc 1, that's a lesson for Calc 2 probably. All right, ciao.